Okay, let's talk now about the pure circuit. So we learned before two circuits, post and takedown. Now we're going to take a look at the pure circuit. As it says here, a pure circuit, it has no side effects, no proof generated, just a hash function. So these pure circuits, we can think of it like normal functions that we can use within other circuits. So this circuit is called public key. And as we learned, it's pretty much a hash. So how do we hash something in compact? So for that, in the standard library, we have this function, which is called persistent hash. In this case, it's a vector of 3. We can go here to the code. We can see we are using a persistent hash, and we are passing a vector of 3 elements of type bytes 32. What are these types? Let's go back here to the diagram. And we have a path, which is also a function available, where we are using this string bulletin board pk, so we can distinguish different contracts, and we are adding, so we have a path of 32. We are passing the sequence, and we are passing our secret key. How we are passing those values? As parameters of the function. So in that way, we can use that pure function in other circuits. By passing these parameters here, we're going to be able to calculate the hash, which is the persistent hash. In this case, passing 3 elements of a vector: this path, the sequence, and the ZK. So this pure circuit, it's used in 2 places. One on chain inside these other 2 circuits, post and takedown, to derive and verify the owner. And then we're gonna see that it's used as well in the off-chain code, in the API's state. So this is something nice about pure circuits. We can actually declare that in TypeScript, so we can simulate things that's gonna happen on chain and simulate it during off-chain code. So we use that to compute its owner locally without a network call. Okay, let's talk now about witnesses. So the witness, it's an oracle that allows us to use private information within our contracts using the witness oracle. So how we declare this oracle? First, we need to use this file, which is called witnesses.ts. And within that file, we have this boilerplate. Before we go into the structure, let's read here some observations about the witnesses. The witnesses is a bridge between your device and the ZK circuit. When the proof server runs the post or takedown circuit, it calls local secret key. The witness reads from local storage. The secret key is used inside the proof computation, but the key itself is never included in the transaction. So that's the magic of ZK. We're using some private information to compute something, and the proof demonstrates that we have run that computation using some private information. So okay, let's see the syntaxes here within this witness.ts file. First, we are declaring the type of our private information. In this case, it's gonna be a type called bulletin board private state, and it has this value secret key of type uint8 array. And now we declare our oracle called witnesses. So it's gonna have a local secret key, and we are passing this context here, which is witness context. We have this function available, and we are declaring here the first value here is the state of our private information, and the second one, it's the new value that we want our private information to be after we have run the circuit. So in this case, the initial private information is private state, and after running the circuit, we want our private information to be the secret value here that we have declared, which didn't change. So basically, it's a way to read the private information, and after running the circuit, we are just gonna place the same private information as before. So in this case, we are not changing the private information. It's just staying the same. Okay, let's talk now about the share API. This is the SDK API that we need to actually interact with the contracts using different providers and instances. So Before this slide, we talk about the contract itself, the logic, how to declare the circuit, create our proof. But now we need a glue, a way to actually use this logic and talk with the different instances. So for that, we're using this share API. And we are declaring that under source index.ts. The library that we are using for this is midnight.js. And this is a really nice library that allows us to abstract all that complexity, talking with different providers and workflows, and we can use simple functions and methods to deploy and run our circuits. Let's read this observation here. The SDK does the heavy lifting. Call TX post, for example, runs the circuit locally, sends inputs to the proof server, packages the proof into a transaction, and submits it to the network. One line of code. So let's see that in an example. So for example, we have this bulletin board API. For deploying a contract, we can see here that we are using this function called deploy contract. We are passing providers, which are the declaration of how we talk with different instances that we have learned before, what these providers means. We are passing the private state. We are passing the instance of our contract, and we are passing the initial state of the contract. And just by running that, we have successfully deployed a contract. You can see how easy it is to actually deploy a contract in the Midnight network. Once we have that, we can declare other functions to run the circuits declared within the contract. For example, in this case, we have a circuit called post and takeDown. How we run those circuits? So when we deploy a contract, we get this instance called deployed contract, and we have some methods available. In this case, we can call transaction, and now we have available the different circuits. In this case, post, we pass the message, and by running that function, all the workflow and interactions, creation of the proof, sending to the node, waiting for the indexer to respond, it's all embedded into that only function. So you can see that using Midnight.js plus the different abstraction methods that we have available in Midnight, it's really easy to run now ZK circuits. The same thing happens for the takedown. We are using the instance deploy contract, calling the method call transaction and calling takedown. And just by running that function, we are running all that workflow of interacting with the node, and we are successfully taking down the message of the bulletin board. Okay, now let's see some reactive state stream that it's really nice with when declaring functions in Midnight. So I'm gonna show here a code just to demonstrate what I'm talking about regarding the reactive state stream. So you can see here that we are using a provider's instance, and we're calling the public data provider. That's our index. And we are getting an observable. So what's an observable? It's an abstraction of a library that we can have reactive information. So whenever something changes on the indexer, we got that information on the client. It's the way it works WebSocket. So we have reactivity. We don't need, the user doesn't need to start to keep refreshing the browser to get updated information. That information, it's updated by itself, and the user doesn't have to do anything. So this is a really nice feature that we have available in Midnight. So we are declaring this observable, and then another piece of information code here, really nice, it's that, you can see that we're using these pure circuits. So we're using that pure circuits to deduce some logic to display on the UI. So this is, as I mentioned here, says is owner computation. It's using these pure circuits, and it's computed entirely on the client. The pure circuit runs the same hash, compares with the on-chain owner, and returns true or false. No server calls, no ZK proof needed, just math. So you can see here how on off-chain code, we are using the declaration of the pure circuits. So something that was declared on compact, now it's available in the TypeScript environment. Okay, let's take a look here at the wallet and providers. We have learned before how to declare these providers for the counter contract, and we can see here that it's really similar for the bulletin board contract. As I mentioned, once we learned how different systems connect and how we declare providers, this is pretty much the same for every contract that we are going to learn. So let's take a look here. So we are declaring the midnight and wallet providers that implements wallet provider, and we are passing the build function as before, and we are declaring functions as balance transaction and submit transaction using methods of the wallet called balance and bound transaction and wallet submit transaction. This is pretty much the same structure that we learned before. This is boilerplate. You don't need to write that all the time from different contracts. It's just a one-time syntax that you have to learn and put in your code, and then you repeat it for other contracts in the future. Okay, let's see now the difference when interacting with a browser in comparison to the CLI. So we have here some code where we can see that we are talking with the Windows object of the browser, but these are some changes that we have to do. But as I mentioned before, all these changes are pretty much the same all the time. Once you have it set it up for one contract, it doesn't change that much for another contract, or it doesn't change at all. So let's see some differences. Here I have made a table where I can see the difference between the CLI application and a UI application. For example, in the case for a wallet, we can see that during the CLI application, it's a self-managed seed. And in the UI, we're using the lace extension to interact with that wallet. For the private state, in the CLI application, we're using the label DB, which persists. And in the UI, we're using in-memory map or local storage. And for the proof server, it's a direct HTTP to the proof server. And in the case in the UI, we are interacting with the proof server through the lace wallet. So that's why it's called URL from lace config. So the same contract, same API, same ZK proof, different wiring. The contract doesn't care which frontend calls it. So this is just a way to declare it in the frontend. You can see here that we have a wallet provider as well, right? But now we are, instead of calling the SDK, we're calling the connected API. We have done a starter template that you can use to create applications, so you don't have to worry about creating the wallet widget and how to get these connected APIs. This has been built by Edda Labs out of the box, so you can have these wallet widgets and all these interactions out of the box. Okay, so let's see how everything connects as a flow. So we have the ZK proof flow recap. User calls API post hello, so we're running a circuit. The SDK runs post circuits locally. The witness injects the secret key from the local storage. The circuit computes order using the hash function, and then it inputs sent to the proof server. So we're using this private information plus the circuit that we run locally. After we get the proof, sending the information to the proof server generates the ZK proof, and the SDK packages the proof into a transaction, and then we use wallet provider balance to add the night fees, and then we run the midnight provider submit transaction to broadcast that to the network, and then the indexer picks that up. We're using that observable state, so our UI renders automatically. So what goes on chain, it's state, the message, the owner hash, the ZK proof. What never goes on chain, it's the secret key. Okay, perfect. So that's pretty much the application of a bulletin board. As a summary, we can remember some specific topics. For example, the pattern ZK ownership. Where is that in the code? We have the assertion function, and it proves ownership without revealing identity. We have the replay protection. So we have this variable called sequence, where we increment by 1 whenever somebody interacts with the contract, and that's a way to all proof becomes invalid after removal. Another pattern that we have are explicit disclosure. So using this disclose within the contract, it's a way that we are saying to the contract, okay, we are okay using this private information to update a public information. Then we have pure circuits. For example, the public key in the state. We can use that in other circuits, but we can also use it off-chain to calculate some logic and demonstrate what's happening on-chain and what could happen that during an off-chain execution. And then we have the provider abstraction. That's going to depend on the application that you're running, if it's a CLI and a UI, and there's a wiring different for each case, but it's just boilerplate. Well, perfect. We have learned a new contract, the architecture, and how everything connects. In the future sessions, we're going to keep learning new architectures, new contracts, new trade-off. So stay tuned.